of the first ever international workshop on programming languages for quantum computing. That's Planck, by the way, as in Max Planck. So thanks on behalf of myself, Mike Hicks, and Shouty Wu, the organizers, for coming. The first talk of the day is going to be, thanks Shouty, as I was saying. The first talk of the day is going to be an introduction to quantum computing from a programming languages perspective. This is especially for the people in the audience who are not already experts in quantum computing. And it's going to be given by Jennifer Paykin, who was the lead developer of the Quire quantum programming language and has done work in type systems, in semantics, and equational reasoning for quantum computing. And yeah, take it away, Jennifer.
Thanks. Can everyone hear me okay? Okay, great. Yeah, I was really excited to give this talk because I started working in this field not knowing anything about quantum computing. It was very intimidating. The last physics class that I took was in high school. I think that, so given that, there you go. So given that, my goal here is to provide some background for the folks in the audience, maybe coming from a PL background, so that you can get something out of these talks today and hopefully learn something new and take something away from this day. So as I sort of have come to find, there is a pathway to learn about quantum computing, which is maybe not so intimidating as it first seems. And I really think that all it takes, you need a little linear algebra and just like an open mind. Of course, that's a vast like exaggeration, because when you take this very simplistic approach that I'm presenting today, there's a lot of subtleties that you might lose out on. I'm going to be making some generalizations in this talk. Please don't get too mad at me. But you can gain those things over time. But I think that this is a good way to introduce the topic. I'm going to sit over here. So I'm going to give this talk in two parts. I'm going to start by talking about how I tend to think about quantum computers, one way of thinking about quantum computers, and then I'm going to give a little quantum programming language and describe the basics of quantum computation as the operational semantics for that language. What is a quantum computer? This is the model that you can have in your head when you think about them. It's a black box. You give it a circuit. By circuit, we'll give some examples later on, but you can really just think of it as a sequence of instructions of things to do. And it's going to give you back measurement results. The quantum computer, these measurement results are classical bits that it's obtained by manipulating its quantum state. But it can't give us back the quantum state directly because that doesn't exist outside the quantum computer. So the only way that it can communicate with us is via these probabilistic measurement results. Okay. This is a really exciting time to be in this field because people are actually building quantum computers. We have over 50 computers with over 50 qubits that are based on a variety of different interesting techniques. There's a lot of really cool research going on the implementation side. Google achieved quantum supremacy, which means that they were able to perform a computation that can't be done on a classical computer, at least in thousands of years. And little asterisks there, but we don't have to worry about that. But the quantum computers that we have are also very noisy and messy, and they introduce errors into the computation. Over the course of today, you're going to hear a lot of talks about NISQ, which is noisy intermediate scale quantum computing. And so the idea there is, what can we do with these quantum computers that we have, or we almost have, that is actually still useful? And we can do, and I think that there is a lot of promise for doing a lot of physics simulations and chemistry simulations and physical systems and things like that. But I'm not really going to get into any of those applications. They're fascinating, but we're here to talk about programming languages. Luckily, there's a whole lot going on in the field of quantum programming languages as well. Because this is sort of still a very developing field, there's a lot of flexibility for experimenting with different kinds of language designs, different kinds of features that are unique to quantum computing. I talked about, we often think a lot about in terms of quantum circuits, which you can think of diagrammatically. They're very compositional. There's a lot of great work going on in terms of all different kinds of semantics for circuits, for languages, operational, denotational, categorical semantics, all that. There's all sorts of tools that are being built for compilers and optimizations so that people can write high-level programs and get out, be confident that their code is going to compile efficiently and actually be able to run someday on a real quantum computer. We could go on and on about all these different topics, but I just don't have time to get into them all right now. So I want to focus down on a simple, particular choice of a quantum programming language and sort of explore what quantum computing looks like from that perspective. Okay, so let's get started. You may have heard the word qubit. Qubits are quantum bits, and they can be, in either states, 0 or 1, just like ordinary bits. These are called classical states. We generally use classical to refer to non-quantum things. We will usually pronounce them ket 0 and ket 1, because these little brackets are the right-hand side of bracket. There's additional reasoning going on behind there, but that's sort of where the word ket comes from, which you might hear. Now, qubits, of course, aren't just ordinary bits. They can be a superposition of these classical qubits, 0 and 1. So the general form of a qubit will have the form alpha 0 plus beta 1, where alpha and beta are complex numbers. And the sum of their squares has to equal to 1. We'll revisit that in a second. So if this is our syntax for qubits, then the semantics is just a vector with these two complex numbers, alpha and beta. Really, this ket 0 is just the basis element 1, 0, and ket 1 is the basis element 0, 1. And if you write this out as alpha 0 plus beta 1, you exactly get this vector. Okay. So that's all we're doing there. Okay, so now that we know what qubits are, great, we can think about the syntax for the beginning of a quantum programming language. So we're going to have some commands, C, and we're going to have a probabilistic operational semantics that takes quantum states to other quantum states with some probability P. Okay, what's going on? What's this probability? Probability comes from the measurement operation. Let's introduce some new syntax, the command measure x, where x is some qubit variable. What does measurement do? Well, if we have a quantum state alpha 0 plus beta 1, that state is going to step to the classical state ket 0 with probability alpha squared, and it's going to step to the classical state ket 1 with probability beta squared. So we said that alpha squared plus beta squared has to equal to 1, so this actually makes sense as a probability distribution. Now, these little diagrams here are two different ways of representing measurement in a diagram of a quantum circuit. So I'm going to put these symbols here so that maybe you can recognize them in future talks. But we can see that the input to both of these separate symbols is a single wire, and the single wire means a qubit, essentially. The right-hand side is a double wire. I think you can see that. And the double wire indicates that this is a classical bit. So because once we've measured the qubit, we get something in a classical state. We get the double wire. OK. So let's think about a slightly more concrete example. Let's say that we measure a state that's in the classical state ket 0. Well, then we can sort of expand that out, where we take alpha to be 1 and beta to be 0. So we see that it steps with probability 1 to ket 0 and probability 0 to ket 1. So all that means is that if we are in a classical state, measuring it isn't going to change that. OK, but not all qubits are in classical states, right? Some are in superposition. So here's a particular state that's in a superposition of 0 and 1 with amplitudes 1 over square root of 2 for each component, right? So if you plug in the numbers, we see that this state steps to 0 with probability 1/2 and 1 with probability 1/2. So it's like a coin flip. It has equal probability of being 0 and 1. OK. Now, some people from a PL background might say, oh, OK, I've read about probabilities and probabilistic operational semantics, and that's kind of a bummer. And yeah, it kind of is. But we have alternatives. So in particular, there's another kind of semantics of quantum programs where we can encode probability distributions over quantum states in a representation called a density matrix. It's a very nice formulation. It means that a program like measure is just now a regular function from a density matrix to a density matrix. So in this example, on the right-hand side, the density matrix with 1 over square root of 2 on the diagonal excuse me, represents probability distribution over ket 0 and ket 1, where they have equal probability 1/2. However, it's a little bit less probably intuitive, just sort of to explain what these density matrices are. So for the purposes of this talk, I'm going to stick to the probabilistic semantics. But density matrices are really great to work with in practice. OK. So we talked about how measurement works on a single qubit. But now what if we have multiple qubits in a system, right? Because otherwise it's pretty boring. For concreteness, let's think about a 2-qubit system, and you can sort of generalize to n qubits. So a 2-qubit system has 4 different basis states. So we have ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1. And their coefficients, again, the squares have to sum to 1. So semantically, this is now a 4×1 vector. In general, it's going to be of size 2 to the n by 1. And these basis elements are just the basis elements with 1 in a single position and 0s everywhere else. So in a similar way, we can write this out. Now, if we have 2 independent qubits, so we already have 2 qubits, we can put them together next to each other. And essentially, they're going to act independently. But the way that we put them together is via this tensor product. It's the usual tensor product from linear algebra. You combine the components in this way, and you get out something that looks like this. You don't really have to worry about the exact coefficients. But it's important to note that not all 2-qubit states or multi-qubit states can be factored in this way. Excuse me. So for example, the Bell state is a state of this form. It's either in the state, so it's 1 over square root of 2 in the state 0, 0, and 1 over square root of 2, 1, 1. So you can write this out as this vector. So this satisfies the property that we saw before, where the sum of the squares sums to 1. But if you sort of write it down on paper and try to work with it for a second, you can pretty easily convince yourself that it can't be factored into 2 separate states. So in this case, we say that these 2 qubits are entangled. Okay. So if we have multiple states, if we have multiple qubits in our state, then we have to amend our little operational semantics thing. So instead of just stepping from a state to a state, states now, unlike in a classical programming language where a state might map variables to values, our state has to contain all of the qubits together because they might possibly be entangled. So we're just going to amend the operational semantics so that a configuration has both a quantum state with possibly multiple qubits in it, as well as an ordering of the qubits so that we know which one goes where. So that's all that I mean by that that list. And everything else is pretty similar. So let's see a little example. If we have 2 independent states and we measure one of them, then doing that measurement is not going to affect the other one, right? So like here, we measure x, and the state of y doesn't change. It's still q sub y. However, if we have 2 entangled qubits, like the Bell pair, then measuring the first qubit is, so even though before measuring x, y is it a superposition, right? We don't know whether it's 0 or 1. It's undetermined. But after measuring x, y is now in a classical state, right? It's either 0 or 1. And that's because the other possibilities, 0, 1 or 1, 0, were not possible. They had 0 coefficient in the original state. Okay. So intuitively, when you have entangled states, measuring one is going to affect the other one. Yeah, okay. Great, we've talked about measurement. So far, we've gotten through one operation. Of course, there's other things we can do on our quantum computers and our quantum programs. We can also initialize qubits. So here I'm going to say that we can initialize a new qubit x. So x here we just assume is fresh, and we're binding it here. And we can initialize x in either the state ket 0 or ket 1. So b is a bit here. And all this does is takes the current quantum state and it tensors on an independent classical state in the state ket b here. Okay. So this initialization operator tells us how we can introduce new classical independent qubits. But of course, that doesn't get us the interesting parts, which are superpositions and entanglement, right? So the way that, one way that you can generate states in superpositions and entanglement is by applying unitary operations or unitary transformations. So these have the form apply an operation u to some list of qubits. And when we draw it graphically as a circuit, u is always going to have the same number of inputs and the same number of outputs. So in our little programming language, it's going to affect the states of x1 through xn, and it's just an imperative operation. You can think of it like that. What does it do? Well, each of these u's corresponds to a particular kind of matrix, a unitary matrix. A unitary matrix is one, it's a square matrix, it's complex values, and it's one so that it has an inverse, and that inverse is its conjugate transpose. So that's pretty cool because all of these operations are really easily reversible, because you just take its conjugate transpose. That's a really easy operation to do. And what the semantics of apply u to x's is just apply the unitary u to the state x's. So notice here that this, as I've written it, this only works when I'm applying u to the same variables x's in the same order that they are in the state. Of course, you can do it to subsets and different orders. You just have to rearrange the state first to make sure everything lines up. OK, so I want to give a couple of examples of unitaries so that you might see them later on in talks and have some idea of what those are. There's many more that I'm not going to mention, but maybe this will give you some idea. So first we have the not unitary operation, also called X sometimes. And its semantics is this matrix here, 0, 1, 1, 0. And you'll see it written sometimes with an X in a box, and sometimes, probably more often, with this O plus around a qubit line. So what does this do? Well, to figure out what it does, all you have to do is sort of expand out applying the matrix. So it, in particular, X takes the state alpha 0 plus beta 1, and it flips the order, right? It transposes where alpha and beta are, and it gives you beta 0 plus alpha 1. So in that sense, if you were to feed it the classical state 0, you would get out the classical state 1. So that's the sense in which it's negation. Okay. Another very common operation that you'll see is the Hadamard transformation. The matrix looks like this. Don't worry about it. It's a box with an H in it. But what it does is that it takes, I'll describe how it acts on the basis states, because then that tells you how you can infer how that acts on the rest of the states because of linear algebra. But if we expand out with the ket 0 state, we'll see that it gives us the state 1 over square root of 2, 0, plus 1 over the square root of 2, 1. So we saw this state before. It has equal probability of, when measured, to be either 0 or 1. But now applied to the state ket 1, you get something very similar, but that negative 1 in the bottom right corner plays in. And so you get 1 over square root of 2, 0, minus 1 over square root of 2, 1. And notice that this also has the property that when you measure it, you have equal probability of being 0 or 1, because you square the coefficients. But they're not the same state, right? Because these one has a negative in it. And in fact, these two states form a basis for the same vector space of qubits. So you can think of Hadamard as changing the 0, 1 basis into this other basis, which we usually write as plus and minus. So it's like a change of basis operator. And so you'll often find yourselves going back and forth in between these two bases. Okay. One more unitary before we move on, which is the controlled not unitary, or CX. Recall that X, we used X for not, so CX is controlled not. And it's represented by this little symbol here, because controlled not is a 2-qubit unitary gate. So it's a 4 by 4 matrix, so it acts on 2 qubits. And what it does is that the first qubit acts as a control. So if the first qubit is 0, then controlled not won't do anything. The control is off. If the first qubit is a 1, then the control not will apply the not operation to the second qubit. So it'll send 1, 0 to 1, 1, and 1, 1 to 1, 0. So this is one of the common ways to entangle 2 qubits, because you're mixing their states together in some informal way. Okay. So I want to talk about one more general idea. And the idea is kind of that this control NOT operation, it's kind of like a control flow, right? It's kind of like, well, if the first qubit is 1, then you do this other thing. It's actually a really interesting topic because this quantum control flow is actually not necessarily realizable if you do it wrong. So you have to be very careful about how you do that kind of control. We can do this controlled unitary gates, but not necessarily controlled arbitrary other operations. But what you can do is if we measure a qubit and you get out a classical bit, essentially, then we should be able to use that classical result to decide what to do next, so to decide which arbitrary circuit to execute. So the way that we think about this is often by extending our quantum circuit model, the picture that we had before, and putting that quantum computer alongside a classical computer, which directs its control flow. This is called the QRAM model. So essentially what will happen is that the classical computer will say, oh, quantum computer, please execute this circuit. And the quantum computer will give us back the measurement results. And then that classical computer can do an ordinary case analysis to decide which of C0 or C1 to execute next. In our little programming language, we can add in some new constructs that do this classical control. So we can have while loops and if statements as long as the conditionals are always measurements, right? Yeah, you might hear the mantra quantum data because we have these qubits, but classical control. Okay. So that's basically the whole language that I want to talk about. Of course, we also have sequencing and skip, but essentially I've presented this little probabilistic operational semantics. As I alluded to before, this is by far not the only choice in programming language design. There's actually a lot of creativity and really exciting things that people are experimenting with in terms of quantum programming languages. We have all sorts of functional language with linear types, with dependent types, which we're going to hear about in the next talk. Embedded languages, different kinds of abstractions, categorical semantics. There's just a really exciting range of topics, I think. So I hope that this introduction has hopefully helped some people and made the topic a little bit more accessible. And I hope you can get something out of the rest of this day. So thank you very much. Any questions?
Hi, I'm Jim Walker, and we already are doing control at the quantum level as well. So I just wondered if you made a distinction there that you're not doing the control. So are you basically submitting, in your paradigm, you're submitting after every measurement then back to the quantum computer? Is that what's happening?
You don't have to send every measurement back to the quantum computer. In fact, that's pretty inefficient, and it's not a very good idea. But the idea is that you could send measurements back to the classical computer if you need to decide whether to, say, continue amplifying a state or making additional computers. So there are, of course, ways to reduce that difference, right? So that maybe the classical memory is really in the quantum computer and you don't have to go somewhere else. But intuitively, that's the thing that you're doing, is making classical decisions versus quantum decisions, I think.
Okay, yeah. Yes, we're basically doing the decision making in real time with we're staying within the context of the quantum computer, basically.
Yeah. Mm-hmm.
Okay.
But we're yeah. So this was just an intuitive diagram. Of course, we don't want to send the data too far.
And the last session today will actually be on exactly this topic, which I think is part of why Jennifer chose to focus on it in this talk. So excited about that. Any other questions? All right, let's thank our speaker.